Alright, so you also need to know about nitrogen. So here you need to be able to describe and write equations for the formation of oxides of nitrogen by the reaction of nitrogen and oxygen at high temperatures. So the place that this links to is combustion in cars. So in places of very, very high temperatures, we're talking about lightning, furnaces in industry and engines in cars. There is enough energy to split this triple bond. Now this value up the top here, 959 kilojoules per mole, this is here really just to show you that's a lot of kilojoules. Right now you don't have a lot to compare that to, and so that number may not make any sense, but that's a lot. So we've got 3 bonds to break, which requires a lot of energy. And that's why it has to happen in really high temperature circumstances. So in aerobic conditions, so in the presence of oxygen and high temperatures, because that's what it requires to get this started, nitrogen gas can combine with oxygen and we get nitric oxide. This nitric oxide is more reactive, so it's able to form to join with extra oxygen molecules and form nitrogen dioxide. Nitrogen dioxide is water soluble, so it's able to dissolve in the water in the atmosphere, so the rain clouds, and this forms then the nitrate ions. So you can see the 3 equations here of how nitrogen gas can be converted into a water soluble compound. This water-soluble compound can then form ions, which is the nitrate ion, and this nitrate ion is able to be taken up by plants. So just a note that this connects to your oxides, and it also connects to acid rain. So when you're having a look at this, you can see that there's nitric acid here, in this part. So we've just got 2 ions. You can see that hydrogen ion, or the proton, is the acid part, and the nitrate ion is what's able to be taken up by plants. So in the wrong situation, this is not an ideal compound to be forming, but in the right situation, it can give nutrients to plants. So what about anaerobic conditions? Well, this happens the natural way. So nitrogen in the atmosphere can be what we call fixed or converted by particular plants. And in this case, we tend to be talking about things like legumes, and they're more commonly known as beans and peas. So these legumes have particular enzymes in this nitrogenase, and it's able to convert N2 into NH3 and NH4, the NH4 plus ion. So this ion is able to be taken up by plants. So the other way that this can be done is through the Haber process. So the Haber process requires a couple of steps. So first, the nitrogen and hydrogen need to be combined, and you'll take a look at a video that shows this in action in a minute, and this forms the NH3 compound. We then get the NH4 plus ion being converted into the NO2 minus ion and back to that nitrate ion that we saw before. Just a note about where else this links in the subject outline. You'll see this again in topic 3 when we talk about chemical industry, and the Haber process is one of the processes that you need to be aware of in chemical industry. So this short video will help you to see the Haber process in action and show you the stages of the Haber process.
One of BASF's first ammonia reactors stands today in Ludwigshafen as an eloquent testimony to the industrial implementation by Carl Bosch in 1913 of the laboratory-scale ammonia synthesis developed by Fritz Haber. The production of this important basic chemical still has its firm place within BASF's chemistry Verbund. To combine the two starting materials, nitrogen and hydrogen, to produce ammonia, the bonds in the diatomic nitrogen molecule have to be broken. Under high pressures of more than 150 bar and temperatures above 400 degrees centigrade, nitrogen adsorbs onto an iron-based catalyst and is split up into atoms. Hydrogen can now be adsorbed and ammonia is produced. The catalyst itself remains unchanged. This reaction generates heat, and therefore the reacting hot gas in the ammonia reactor is cooled with a supply of cold gas. This is achieved with a sophisticated flow system of synthesis gas based on the heat exchange principle. In this way, the so-called equilibrium reaction can be prevented, in which the ammonia tends to decompose again to its constituent elements. The ammonia is collected as a liquid and stored in tanks. The remaining synthesis gas is returned to the reactor and forms more ammonia. An important precondition for ammonia synthesis is the efficient production of pure hydrogen. In several process steps, this precedes the actual ammonia synthesis. In the primary reformer, first the natural gas methane is heated together with steam to about 800 degrees centigrade and is thereby converted into a mixture of carbon monoxide, carbon dioxide, and hydrogen. In the downstream secondary reformer, air is then added and the remaining methane gas is converted at above 1000 degrees centigrade by means of catalysts, and nitrogen is added. Since especially carbon monoxide but also carbon dioxide would damage the iron catalyst used in the ammonia synthesis, they have to be separated off. Carbon monoxide is converted into carbon dioxide in a two-stage process using special catalysts. The carbon dioxide can be removed by a chemical scrubbing process. What remains is the pure synthesis gas consisting of 3 parts of hydrogen and 1 part of nitrogen, which can now be transferred to the actual ammonia reactor. A good 3/4 of the global output of ammonia goes into fertilizer production, while the remainder is used for technical products.
Alright, so the other thing that you need to be able to do is describe how the nitrogen cycle operates by natural processes such as lightning and nitrogen-fixing bacteria and decay, and industrial processes such as the Haber process to make fertilizers and combustion reactions. So there are lots and lots of really good diagrams and flowcharts to help you understand the nitrogen process. I've got about 10 here and I like different parts of all of them. So I think these diagrams are quite good at showing you details of what's going on in this one, and I particularly like that this has got the Haber process included. And you'll find these in a folder called Nitrogen Cycles on Moodle. So go through and have a look and see which ones you like the best. So there's a short clip giving a lot of detail about the nitrogen cycle and following it through. Be aware that some of the equations given are extra breakdown equations and you need to only know the ones that you've already seen. This is an overview of the nitrogen cycle. It shows all the processes that take place in the nitrogen cycle that you'll need to know for your exam. You can see that it's very complicated and we're going to break it down into the parts now. This is nitrogen, as you've probably seen it before. You can see here that nitrogen has a triple bond. Nitrogen in its gaseous state takes a lot of energy to break because as you break each bond you need to have lots of energy. So there's 3 bonds to break, so in total we need 3 bonds worth of breaking energy. As we just said, it takes a lot of energy to break a nitrogen bond, so it requires things with high heat. So things like lightning, volcanoes, or industries with furnaces. Anywhere where there's a lot of heat and a lot of energy. So the process of nitrogen breaking through these high heat means that it reacts with oxygen in the air. So we have nitrogen reacting with oxygen to form NO. This process repeats with more oxygen in the air. So we have nitrogen oxide reacting with oxygen to form NO2. This then reacts with the water in rain and goes into lakes and underground. From here, plants take it up, and this becomes nutrients for the plants. Large amounts of heat and energy are not the only way that nitrogen can get transported to the ground. So a Haber process is a process by which the nitrogen in the atmosphere can get broken down into NH3 and from there oxidised by bacteria to form NO3, which is water soluble and can be taken up by the plants. The Haber process is outlined here. We have the nitrogen reacting with hydrogen under high heat to form N2H2. This is then reacted with more hydrogen to form N2H4, and this is reacted with even more hydrogen to get NH3. Have a think about whether this process is aerobic or anaerobic. It's really important for it to get to this ammonium stage because we have this process of oxidization that allows it to be water soluble. Keeping in mind that plants can only take up water soluble products through the soil. Similarly, there are nitrogen-fixing bacteria. These are found in special plants called legumes. An example of legumes are peas. This process is similar to the Haber process in the sense that we get NH3 and then this is oxidised into the soil. As this is a cycle, there needs to be ways of the nitrogen being converted back into N2, or gaseous nitrogen. So some other things that happen. Plants provide protein for animals. So the plant protein gets consumed by the animals. From the animals, there's anaerobic decay, and that turns it into NH3. There's also waste products from the plants.
Hydrogen sulfide gas is released into the atmosphere by volcanic eruptions, hot springs, and anaerobic decay of sulfur-containing biological material in swamps, bogs, and tidal flats. Certain marine algae produce dimethyl sulfide, a volatile compound that enters the atmosphere as tiny droplets. Sulfur dioxide gas is released into the atmosphere by volcanoes and also forms when dimethyl sulfide reacts with oxygen gas. The burning of fossil fuels, such as coal and oil, releases sulfur dioxide into the atmosphere. Sulfur dioxide reacts with atmospheric oxygen to produce sulfur trioxide. Some sulfur trioxide reacts with tiny water droplets to form sulfuric acid. Sulfur oxides also react with ammonia to produce tiny particles of ammonium salts. The winds carry droplets of sulfuric acid and particles to sulfate salts, which then fall to the earth in acid deposition. By adding sulfur compounds to the air, the use of fossil fuels increases the rate of acid deposition. All living things require sulfur to make proteins. Plants get sulfur by taking up ions of sulfate salts from the soil. Animals get sulfur by eating plants, and all living things release sulfur compounds when they decay. Decomposition releases sulfate salts, which can be taken up by plants, as well as gaseous hydrogen sulfide. Some hydrogen sulfide enters the atmosphere, but when decay occurs in an oxygen-free environment, Anaerobic bacteria break down hydrogen sulfide and release sulfur gas. Oxygen-requiring bacteria can incorporate sulfur into sulfate salts, which can be taken up by plants and enter the food chain once again.
The last of the biogeochemical cycles we'll be talking about this chapter is the phosphorus cycle. I like to do this one last because in a lot of ways this is the simplest cycle that we've talked about so far. The reason this one's easy is if you look up here at the atmosphere part of the cycle, there are no arrows coming towards or leaving from the atmosphere, which means there is no atmospheric stage to the phosphorus cycle. Everything is taking place either in the soil or in the water, somewhere on the ground that keeps it out of the atmosphere. And I think the complicated parts of the nitrogen cycle and the carbon cycle are what moves those two particular elements to or from the atmosphere. So the key to this one is this stuff. It's all in, as it calls in this diagram, the mineable rocks. It's all in the minerals. There's two ways that phosphorus gets out of the minerals. One of the ways is weathering, the other one is mining. The weathering idea could be erosion, anything that's breaking down those rocks and making the phosphorus available. The material that's weathered out of the rocks is either going to go into rivers or directly into the soil. When it's in the soil, it gets uptake into land plants, and then those plants are eaten by consumers. So that's ultimately the way that we get all of the phosphorus that we need. It comes from the vegetables and things that you are consuming. Those consumers then can eventually decompose and go back to the soil, and that kind of creates its own little mini cycle over on the side. It's the same general approach in the ocean. The producers are getting it from the water itself, and then they're eaten by consumers, which eventually die, go down to decomposers, and that keeps on going in its own little cycle as well. So the phosphorus cycle is ultimately pretty simple compared to the other two. Just like in the previous cycles, we always have to talk about human impact as the last stage. You can see here fertilizers and detergents is the main way that people impact this cycle. If you use dish detergent, laundry detergent, things like that at home, that contains a lot of phosphorus in it, and that eventually has to go through a wastewater treatment plant in order to get removed from the water before that water can be released into the environment. Like anything else, too much of a good thing becomes a bad thing. Phosphorus is required for plants to be healthy, but a lot of it really allows algae to take off and do very, very, very well. So well, actually, that it can deplete a lot of the oxygen from an environment because it's thriving so much. So phosphorus is one of those things that people are producing in high amounts, but we do have to be careful about how much of it we're releasing into the environment, because it is something that should be released slowly. If you think about how it's originally getting there naturally, it's coming out of these mineable rocks, it's coming out of minerals, basically, that are broken down through weathering. So as people go through and release things faster, we kind of unbalance this cycle a little bit. Overall, I think this is probably the simplest one, just because, again, there is none of that atmospheric stage in the phosphorus cycle. So this concludes our study of the biogeochemical cycles. Remember, we have water, carbon, nitrogen, and phosphorus. As always, thank you for watching.